All right, we're trying to determine whether each series converges absolutely, converges conditionally, or diverges. So in these kinds of questions, it makes sense to start with the absolute value of the sum. So I'm going to check absolute convergence first. So I'm going to check the convergence of the absolute value. So I want to look at the sum of the absolute value of -1 to the n plus 1 over 3n. So that -1 to the n plus 1, sometimes it's 1, sometimes it's -1, depends on the value of n you're plugging in. So, but since I'm taking absolute value, it's just always going to become 1. So this is actually the sum, n equals 1 to infinity of 1 over 3n. And then we can pull the 1/3 right out of the summation. So this is 1/3 the sum from n equals 1 to infinity of 1 over n, which we know diverges. It's a p series with p equal to 1. Because it's a p series with p equal to 1. Okay, so this is definitely not absolutely convergent. So I have to move on to testing the alternating version of this series. So if I look at -1 to the n plus 1 over 3n, I can still pull the 1/3 out. So this is 1/3 times n equals the sum from n equals 1 to infinity of -1 to the n plus 1 over n. That is the alternating harmonic series, which we looked at in the demo. We decided it converged by the alternating series test because the terms go to 0 in absolute value and they are decreasing. Okay, so because the absolute value of the terms, -1 to the n plus 1 over n, which is just 1 over n, are decreasing to 0, the sum converges by the alternating series test. Okay, so the alternating version of the sum converges, but the absolute value version of the sum diverges. So this is conditionally convergent. Okay, so in this next one, 3 times -1/2 to the n. Again, I'm going to start with the absolute value version of the sum, because if that converges, then so does the alternating version. So I would only have to do one test. If it fails to converge, then I have to test the alternating version separately. Okay, so I'm going to start with the absolute value of my sum. Take the absolute value of each of the terms. Okay, so -1/2 to the n, that's just going to alternate signs. So I can take that negative right out because we're taking an absolute value. So this is the sum, n equals 1 to infinity of 3 times 1/2 to the n. And this is a geometric series. With a multiplier of 1/2, which is between -1 and 1, so it converges by the geometric series test with my multiplier of 1/2 between -1 and 1. All right, so my series converges in absolute value, which means that the alternating version will also converge by the absolute convergence test. So this sum is absolutely convergent. So let me write this all down. By absolute convergence test, the alternating version of the series also has to converge because the absolute value did. So my original sum that I was asked about is absolutely convergent. The sum itself converges. The sum of the absolute values of all the terms also converges, so we call that absolutely convergent. Okay, number 3. The sum from n equals 1 to infinity of -1 to the n times n factorial over 5 to the n. So I'm going to start with absolute value. So the -1 to the n is just going to cause the signs to alternate. And since I'm taking absolute value, all the negative signs become positive. So this is just the sum of n factorial over 5 to the n. So I'm looking at the absolute value of this sum. And whenever you have factorials and exponentials, we're going to use the ratio test. Okay, so the ratio test says take the limit as n goes to infinity of the absolute value of the n plus first term over the nth term. Okay, so the n plus first term means replace the n's with n plus 1's. So this is n plus 1 factorial over 5 to the n plus 1. And then I'm going to divide by the nth term, so that is n factorial over 5 to the n, all in absolute value. Flip and multiply. Okay, so 5 to the n over 5 to the n plus 1 just reduces to 5 to the first. And n plus 1 factorial over n factorial is n plus 1. So this is going to be n plus 1 over 5. And the limit as n goes to infinity of n plus 1 over 5 is infinity. Okay, when the ratio test gives you a number larger than 1 or infinity, the series diverges. So my sum of n factorial over 5 to the n diverges. All right, so that means I have to test the alternating version of the series separately. So I'm going to use the ratio test for that too, which means I'm going to take the absolute value of a sub n plus 1 over a sub n, but this time I'm using that as my, those are my terms. So I have -1 to the n plus 1 times n plus 1 factorial over 5 to the n plus 1, and then divided by the nth term or multiplied by the reciprocal of the nth term. So 5 to the n over -1 to the n times n factorial. All right, so now I'm just going to simplify this. So I have 5 to the n over 5 to the n plus 1. That's going to leave me with a 5 in the denominator. I have n plus 1 factorial over n factorial. That's going to leave me with an n plus 1 in the numerator. Okay, and then I have -1 to the n plus 1 over -1 to the n. Subtract the exponents and you get -1 to the first in the numerator. So I've got a -1 here. But since this is all an absolute value, this is the limit as n goes to infinity of the absolute value of all this stuff. That -1 doesn't matter at all. And I get n plus 1 over 5 when I take absolute value. and that is infinite, which means that this sum also diverges. -1 to the n times n factorial over 5 to the n diverges. Okay, -1 to the n over n squared plus 1. I'm going to start with the absolute value, because if the absolute value converges, so does the alternating version. So I might be able to save myself some work. So I want to look at the sum from n equals 1 to infinity of the absolute value of -1 to the n over n squared plus 1. And when you take the absolute value, this -1 to the n becomes 1 to the n. It's either -1 or 1, and then take the absolute value and you get 1. So this is the sum of 1 over n squared plus 1. And I can do a direct comparison test for this. You can also use the limit comparison test, but direct is pretty easy in this case. Okay, so I'm going to note that 1 over n squared plus 1 is always smaller than 1 over n squared, because we're making the denominator a little bit bigger, which means the value of the fraction will be smaller. So the sum of 1 over n squared plus 1 is smaller than the sum of 1 over n squared, because all of its terms are smaller, so the final sum must also be smaller. And the sum of 1 over n squared is a convergent p-series. So being smaller than something finite means you're also finite. So the sum of 1 over n squared plus 1 converges. Which means the absolute value converges, so the alternating version will also converge, which means that this series is absolutely convergent. Sine n over n cubed. Start with the absolute value. Well, the sine of n is always trapped between -1 and 1. And if you take the absolute value of the sine, it will always be less than 1. So the absolute value of sine n over n cubed is definitely less than 1 over n cubed. The absolute value of sine n will always be smaller than 1. And the sum of 1 over n cubed is a convergent p-series. So the sum of the absolute value of sine n over n cubed also converges by the direct comparison test. And since this converges in absolute value, the sum converges absolutely convergent. So the sum of sine n over n cubed is absolutely convergent. Okay, last one. Start by looking at the absolute value. I like to start with the absolute value because if it converges, I'm done. I don't have to test the alternating series. If the absolute value converges, then so does the alternating version. Now, if the absolute value diverges, you have to continue on and test the alternating version to see if it converges without the absolute values. So my -1 to the n plus 1 just alternates the sign. So when I take absolute value, I can just make that a 1. This is the sum of 1 over n ln n. One over n ln n is always decreasing and always positive, which means I can use the integral test. So whatever the integral does from 1 to infinity, the sum will do. And I'm actually going from 2 to infinity here. So if this integral converges, so does my sum. If this integral diverges, so does my sum. 1 over x ln x. Okay, so I think a u substitution is going to be appropriate here because the derivative of ln x is 1 over x, and 1 over x shows up in my integrand. So I'm going to let u be ln x, which means du dx is 1 over x, which means dx is x times du. So I'm going to head over to my integral. The integral of 1 over x ln x dx. I dropped to the bounds here. I'll put them back on after I have the antiderivative. Is equal to 1 over x times u. And then instead of dx, I have x du. And the x's cancel. So this is, oops, sorry, forgot the integral sign. This is the integral of 1 over u du. And the antiderivative of 1 over u is ln u. So this is the ln of u plus c, and then replace the u with an ln x. So this is the ln of x plus c. All right, so now I can plug in my bounds now that I have an antiderivative. So the integral from 2 to infinity of 1 over x ln x dx is the antiderivative evaluated from 2 to infinity. So this is the ln of x evaluated from 2 to infinity. That means the limit as b goes to infinity of the ln of x from 2 to b. So first I plug in b, then I plug in 2, then I take the limit. So when I plug in b, I get the ln of b, and then I plug in 2, and I get the ln of 2. Okay, now take the limit as b goes to infinity. The ln of b as b goes to infinity is going to approach infinity, and the ln of that will also be infinity. So this is going to be infinity minus the ln of 2, which is still infinity. So the integral diverges, which means so does the sum. So by the integral test, the sum of 1 over n ln n diverges because the integral did. Okay, so that was the absolute value of my original sum. My original sum had an alternating sign. I took the absolute value, used the integral test, it diverged. So that means I have to go back to my alternating version and see, does that converge or not? So I want to look at my original sum, -1 to the n plus 1 over n ln n. n equals 2 to infinity. All right, let's write out a few terms. If I start with n equals 2, I get negative 1 over 2 ln 2. Then I get positive 1 over 3 ln 3, negative 1 over 4 ln 4, positive 1 over 5 ln 5. And as n goes to infinity, the ln of n goes to infinity. So these denominators are just getting bigger and bigger and bigger, which means the terms are approaching 0 and decreasing. So the absolute value of the terms which is 1 over n ln n. So the terms are decreasing towards 0. So the sum converges by the alternating series test. The terms alternate signs, and then the absolute value of the terms are decreasing towards 0. Converges by the alternating series test. So the absolute value of the sum diverged, but the alternating version converged. So that means that my sum, my original sum, n equals 2 to infinity of negative 1 to the n plus 1 over n ln n, is conditionally convergent. It converges, but the absolute value version does not.